as mentioned before in my introduction, you know, we have some variables that can be described as having discrete probability distribution. Why? Because we can really count the number of possible values. However, this count is very high, okay, that you can say that it's almost a continuous distribution. So we can approximate its discrete distribution with a continuous distribution. And from real life examples, statisticians found out that in many of these cases, we can use the normal distribution to describe a discrete random variable. And this is a good news because of the characteristics of a normal distribution, as you're going to learn next. Okay, so what do we know about normal distribution? First, you should know that it's the most important distribution at all, widely used in research and in the practice in the industry. And it is very, very crucial for statistical inference. And you're going to learn that when we start our topics about statistical inference, like hypothesis testing, for example. For now, I'm not going to say more, but just you need to understand that this is very, very important distribution. And what do we know about normal distribution? We know its probability density function. It looks like that. Okay, don't be overwhelmed with this complexity of this PDF. You're not going to use it as is. In fact, we're going to use some tables, but you should know that these tables were derived from this function. Okay, what do we know about some of these, the elements of this function? You know, this is pi, which is 3.14. What's that? This is standard deviation. You know about that. And this is mu. Okay, and mu and sigma, these are the parameters of a variable with normal distribution. Whenever you want to describe a variable that has normal distribution, you give two parameters, mu and sigma. So once you know these two, you can derive its probability density function and you can draw it. Okay, and then you can use that curve that you have drawn to find the probability of x being within a certain range. Okay, as we learned before, this is the power of PDF. So let's move on. So when we plot the PDF of a normal distribution, we get a curve that has a very specific shape, and we have already discussed that when we learned the empirical rule, if you remember, and even when we were discussing the different forms of histograms. So it looks like that. So we have a variable x, and this will be the curve representing its PDF. Okay, so remember, this is the PDF curve, the area under which represents the probability of x being within a certain range. Okay, and this curve, you can see that it's symmetrical and symmetrical around the mean of x. Okay, here we go, mu is the mean of x. So the symmetry of this curve is very important. We're going to use that property later on. But before I proceed, I just want you to remember, guys, many students don't realize that this horizontal line here, this is an axis, like any axis that you used before in math. Okay, and why this is important? It is very important for you to understand that the value of x, for example, here is a value that's smaller than a value of x here. Okay, and remember that x is a variable, so it can take any one of all these values. Okay, and it is continuous, that it can be anywhere on this horizontal line. Okay, and how I'm going to use this PDF, for example, if I'm interested into that value, all right, to find the probability that x is less or equal than this value, this is what I do, and then I find this area, right? Because this is the area under the PDF, which gives me the probability. Now, we call that a bell shape. Why? Mainly because of these two tails going asymptotically around the horizontal axis. Okay, so we have the peak here in the middle, and then we have these two tails which give it the shape of a bell. This is why the normal distribution is widely known as the bell-shaped curve. Let's examine the effects of the parameters, the two parameters of a normal distribution on the curve or on the shape of the curve. So we agreed that whenever we are describing a variable x that has a normal distribution, we should know what are the parameters of this distribution, and the parameters are the mean and the standard deviation. So the mean is mu, standard deviation is sigma, and we denote this variable as, or we use this notation. So this is our variable x. We use this style to represent that this is a probabilistic variable, can take any value, and this is the type of the distribution, which is normal in this case. If it was uniform, for example, I could have used the letter U. Now this is normal, and in normal distribution, then I open here the parentheses and I have to write down here the two parameters of this distribution, which is represented by the mean and the standard deviation sigma. Okay, so let's see the effects of mu on the curve. For example, if variable x has normal distribution with a mean of 20 and standard deviation of 5, so I will represent its PDF like that. You can see that the PDF is symmetrical with respect to the mean, and the mean here is 20. Okay, this is one parameter of my distribution. Now, what if x or the same x or different x has the same standard deviation of 5? Okay, you can see here it's 5, same as above, but now the mean is 25, and I want to plot its PDF on the same axis. Here we go, it shows like that. The curve has shifted to the right. Why? Because the mean has shifted by 5 values, or 5 points. What if x is also have the same standard deviation, but the mean now is 30? Okay, so what would happen? Again, the curve will shift further to the right. You can see now that the mean of 30 is okay at the middle of this last curve. Okay, so what about the effects of the standard deviation? In the previous slide, we have seen that for the same standard deviation and different mean, we can see the effect of the mean on the curve. So also here now we are referring to a variable x with normal distribution. The two parameters are mean and standard deviation. So let's see how does a variable with a mean of 25, standard deviation of 5 look like. It looks like the bell-shaped curve again. We don't have anything here to compare to, but now if I want to observe another variable that has the same mean, but now the standard deviation is 3, what does it mean? We have explained that before. Again, when we talked about the histograms, the empirical rule, that when the standard deviation is less, that means the variability is less, right? So you expect that more of your observations will be concentrated around the mean. So that's why when you plot that, you see something like that, right? The variability is less, which then is represented by a narrower curve. This orange curve, it's much narrower than the blue curve that has standard deviation of 5, which is bigger than 3. Let's see more the effects of standard deviation. and when the standard deviation is 8. So tell me, what do you think? What do you expect the third curve to look like? Of course, we will have much wider curve, so it looks like that, okay, because the variability is much higher. And this is very important for us. Why? Because this will represent, or this will have a great effect on the concentration of the observations around the mean. You're going to see that when we start solving some problems. So now that we have learned about the nature of the PDF of a normal distribution, and we know that the area under this function or this curve can be used to find the probability of a range of values of that x. So let's see how we are going to do it. We have already learned that the function, the PDF function, is very complex. In order to find the areas under the curve, it would be very complex to use that function, because it's not as simple as the uniform distribution. So we're not going to follow the same procedure that we have done in the example of a uniform distribution. Instead of that, we're going to use a probability table. Okay, so it's a table that for specific values of x, we're going to see what would be the corresponding area. However, because we know that a normally distributed variable has two parameters, mu and sigma, then it would be really very not practical for us to have a table for every combination of mu and sigma, right? Because if I want to prepare a table for that, I have to think about all possible values of mu and sigma and prepare a table accordingly. But the good news is that we don't need to do that. Statisticians came out with a very clever way to avoid doing that, and they came out with what we call the standard normal random variable. Okay, this is very important for us. Why? Because then for any variable x, I can standardize it. I can find its corresponding standard normal random variable. Okay, and for only one variable called the standard normal random variable, which is only one of them, that there's no two variables that are called the same. Okay, sometimes it's called the unit normal random variable, and we denote it by z. And statisticians prepared a table for that one. And the question is, then how can I use this table to find the area for a variable x that is not standard normal random variable? What we're going to do, we will standardize that x. And this is what we're going to learn next.